Hello. This lecture will cover pages 287 through 291 of my lecture notes, so please print those pages out and have them in front of you as I present this lecture on MSI Logic Circuits Chapter 9, Part B, Encoders. Starting on page 287, the encoder. The opposite of decoding is encoding. An encoder is a combinational logic circuit that accepts a set of inputs, only one of which is active at a given time, and produces an n-bit output code depending upon which input is active. Here's the block diagram of a general encoder. I want you to notice it looks pretty similar to a decoder. However, here is your data lines. And these data lines right here will determine the amount of output lines that you have. On these input lines, only one of these inputs will be active at any given time. And on the output, they'll produce an encoded form of that input data line. It's just the opposite of what decoding was. Notice I have two enables here, and I'm showing them both high true. For n output lines, we have 2 to the n possible inputs. That's similar. And the enable inputs can either be low or high. I'm showing them as high here. Here we have an example of a binary encoder with low active inputs. And I'm going to look at the textbook here on page 200. In my lecture notes, it's page 287, but you might be able to see this better here if I'm pointing out. This is a logic circuit for an octal to binary or an 8-line to 3-line encoder. Here's our 8 inputs. Only one of these inputs can be active. Remember that. And they're low active here. They're showing the inputs as low active. And these low active inputs, one of them will be low, and it'll produce an output code which is the binary equivalent of the input. And notice we're limiting ourselves here between 0 and 7, so this output's going to be limited between 0, 0, 0, and 1, 1, 1. So that makes it octal. Only has 8 different output states. I want you to take a look here at this truth table, this function table right here. I want you to just notice that these are low active here, and here's our inputs. And on each one of these inputs go low active, it produces an output code, an encoded form of that input. Example 9.5 in the textbook. I have this in the lecture notes as well. I want you to make sure you look over example 9.5. Priority encoders. I want you to read with me. The last example we just looked at identifies a drawback of the simple encoder circuit. When more than one input is active at one time. Well, when we have more than one input is active at one time, this circuit doesn't work. The previous circuit doesn't work. It's assuming only one input can go active. A modified version of this circuit called a priority encoder, and they're used a lot in the digital world, includes the necessary logic to ensure that when 2 or more inputs are activated at the same time, the output code will correspond to the highest numbered input. For example, when both A3 are low and A5 are low, the output code will be 5. Similarly, when A6 is low, A2 is low, and A0 is low, the output code will be 6. That's all taken care of inside this priority encoder. So when you purchase these as an integrated circuit, you'll see that in a minute. That priority encoding is taken care of inside the chip. And you can take a look at it here. This is the truth table for that. These come in many different families. It's a standard 74148 priority encoder. It's a low power Schottky if you need low power and high speed, 148. And it's a high speed CMOS if you need high speed and very, very low power CMOS, 148. Example 9.6 on the next page. Make sure you look that over. And we're going to talk about this switch encoder because we're going to use it in the next circuit. This figure here shows a switch encoder. You can read about it, but basically you purchase this as a 74 LS 147 decimal to BCD priority encoder. So basically here's your 0 through 9. This is an encoder, so only one of these are going to go active. It's a priority encoder, so only one of these buttons you push, and based on whatever button you push, you get a low active output. Notice it gives you the low state here. But I'm just using these inverters here. If you put these inverters in place, they don't come with the chip now. The chip gives you a low output. In other words, if you push a, let's see here, if you push the 6, you'll get a 1, 0, 0, 1 if you push the 6 button with this LS 147. But we just use the inverters here, so when you push the 6, the normal BCD is a 0, 1, 1, 0. That's all this decimal to BCD switch encoder does. LS74147. Now what I want you to do here, and you're responsible for this. This is probably the most important part of this lecture. It's page 290 and 291 in the lecture notes. So make sure you have page 290 out so you can follow this after I go through it. I'm going to go through the sequence of operations to enter a decimal number 309. And that's what they do on these next 2 pages of your textbook. I'm going to show you how this circuit works. I'm going to try to get most of it on here. We're going to put in a 309, and I wrote it here in the book so you see it. Notice this circuit right here is comprised of a decimal to BCD priority encoder. We have some logic gates here. Here's our one shot that has an unstable state of 20 milliseconds. We designed for something like that. It's pretty easy for the engineer to design this. This circuit here will go, it's normally going to be low, and then it shoots high for 20 milliseconds and it goes low. Produces an output pulse for 20 milliseconds and it goes back to its stable state where that's low. Notice we have JK flip-flops here. We're just going to use that as a ring counter. That's connected as a ring counter to generate different clocks. You'll see that in a minute. And we have a clear circuit, and here's our D flip-flops. There's 3 different sections here. These 4 right here, okay, will give us 0 through 9 for a first digit. These 3 here will give us 0 through 9 for the middle digit, and these 3 down here are the least significant digit. They'll give us 0 through 9 here. But what we're going to do is we're going to press 309 out here. And what we're going to end up with is a 3 up here in binary, BCD if you will, binary coded decimal. We're going to end up with a 0 here, and we're going to end up with a 9 here. We're going to capture that in this keyboard entry circuit for a 3-digit number. So how does it work? You're responsible for understanding this, but let's take a look here. And you could read all this on your own on page 200 and 291, but you push this clear. This is a momentary clear button. You push the clear. This is normally high here. This line's normally high. It's pulled up to 5 volts. When you push this clear to start out with, what it does is it clears this JK flip-flop to a 0. It clears this asynchronously right away to a 0. And it presets, if you follow it around, it presets this to a 1. So you set up your ring counter as a 0, 0, 1. Similar to the way you'd have done this on a previous quiz. I'm pretty sure I asked you to put this type of circuitry in to set up the initial 1 condition. Notice it also goes this low when you push this button. It also goes low and it clears all these flip-flops. You end up with zeros the whole way down through all 12 of these outputs. Q0 through Q11, all 0. Then you release that button. Now you're ready to enter the digits. The first thing we're going to push is the 3 out here. When you push this 3, you already know how this LS147 works. And I'm not really concerned about the low active. Here's the true outputs right here, with this being the least significant bit and this being the most significant bit up here. So when I push a 3, it's going to put in a 0, 0, 1, 1. That's a 3. Now, this 3 gets set up here as a 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. So there's 3 set up for this, there's 3 set up for this, and there's 3 set up for this. Only one of them are going to get loaded, though. Let's see what happens. At the same time, when this goes to a 1 here, that 1 goes through this OR gate, and that 1 produces a 1 here, which is a clock, which fires this 1 shot. So the output goes high, and it's high for 20 milliseconds. That 20 milliseconds is a more than enough time for all this 3, 3, 3 to get set up. Remember the setup time? You have to allow for time to this get set up and stabilize on the input here. And then this goes low. When this goes low back to its steady state, back to its stable state, that clocks. It clocks this ring counter. And that 1 that was set up here initially with that clear gets clocked out to here. That goes to a 1. When that goes to a 1, follow it. That's the clock for this, 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 and this. So that 3, that 0, 0, 1, 1 gets loaded. 0, 0, 1, 1. And you have your 3 there for your BCD. That goes to your BCD to 7-segment decoder, which you already designed for me, and the 3-digit lights up on the panel. What's next? You push 0. When you push 0 here, none of this is active here. None of this is active because this button's down here. So you push this to 0 right here, and this stays at a 1, 1, 1, 1. That puts a 0, 0, 0, 0 out here. So 0 gets set up here, 0 gets set up here, 0 gets set up here. But that 0, when you push it, it makes that go to a 1 out here. That is going to fire that 1 shot. So that 0 all gets set up, all the transients die out. Let me show you what I mean by that, because that's important. Whenever you set up an input to a flip-flop, here's a D flip-flop. We're going to set up that input, and you set it up like this, and you go to a 1, or you go to a 0. It doesn't look like that. There's a transient. It goes like this. It rings because of the inductance and capacitance in all the wires. That's why you have to allow for setup and hold times on these flip-flops we talked about. But be that as it may, if you look back here, this goes high for 20 milliseconds. That 20 milliseconds is more than enough time for that 0, 0, 0. It all gets settled out here. That goes back to a low. When that goes to a low, it clocks that. This is a ring counter. There's a 1s here. That 1 goes from here to here. Look what that does. That clocks this, 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 and this. So that 0 only gets put here. Doesn't get put in these other registers. So now you have your 3 here. It lights up through your BCD to 7-segment design. You have your 0 here. It lights up on your 7-segment display through your BCD to 7-segment display. And now you push a 9. We push this 9 right here. This goes low. Let's look at the outputs out here. 1, 0, 1, 0. There's your 9 that gets set up. It gets set up here, it gets set up here, and it gets set up here. When these go to 1, I don't care which one going to 1, that one or this one. It doesn't make any difference. They both go to 1 here and here. But those 1s produce a 1 here. It fires the 1 shot. 20 milliseconds later, it allows this 9 to get set up. The set times for 20 milliseconds. You have your setup. And then this goes low. When this goes low, it clocks that 1 to here. Remember that ring counter is just passing that 1 around. When that 1 goes to here, when this goes high, look where that line goes. Clocks this one, this one, this one, this one, and you get a 9. 1, 0, 0, 1. Goes through your BCD to 7-segment decoder, and you're displayed on your panel 309. That's how this circuit for the keyboard entry of a 3-digit number is implemented. And all that is explained in your lecture notes on page 291 or on the next page on your textbook when you find it in your textbook. That's an important application. The reason I like it, and the reason I want you to go through this on your own and make sure you understand it, is because it uses an encoder. It uses combinational logic. It uses that one shot. It uses a ring counter. It uses the D flip-flops as storage registers. It ties a lot of things together. And that concludes this lecture.